It's a great pleasure to introduce today's speaker, Sammy Sbiti from University of Pennsylvania, that will talk about on the Ricci flow of homogeneous metrics on spheres. Thank you, Sammy.
Okay. So thank you for the introduction and thank you for inviting me to speak. So today I'll talk about the Ricci flow of homogeneous metrics on spheres. So first, a little bit about the Ricci flow. So a Ricci flow is a one parameter family of metrics whose time derivative is minus twice the Ricci tensor. So up to a time-dependent family of diffeomorphisms, the Ricci flow is equivalent to a parabolic PDE. And so similar to the heat equation, it has regularizing properties for Riemannian metrics, which makes it useful for proving classification type theorems in geometry and topology. So for example, when Hamilton first developed it, he used it to prove that three manifolds with positive Ricci curvature are space forms. Later on, Bowman-Wilking used it in their proof that manifolds with positive curvature operators are space forms. Brendel and Schoen used it in their proof of the quarter-pinch differentiable sphere theorem. And of course, Perelman used it in his proof of the Poincaré conjecture. So typically, the Ricci flow develops singularities. And one way to overcome these is by performing surgeries. But in order to do this, it's important to understand what these singularities look like. And one usually does this by some kind of blow-up procedure. So you take a sequence of points and times where the curvature blows up, and then a sequence of parabolically rescaled flows around these points. Then you try to take some kind of limit. So when you do this, then in the limit, you get a new solution to the Ricci flow in a possibly different space, but one that's defined on a time interval from minus infinity to 0. So such solutions that are defined from minus infinity to 0 are special, and they're called ancient solutions. So again, the Ricci flow being equivalent to a parabolic PDE, for generic initial data, the backwards equation is not well posed. So being able to go back in time even a little bit is special. Okay. So in today's talk, I'm going to specialize to the case of homogeneous metrics on spheres and see if we can completely describe the behavior of the Ricci flow in that case. So I'll discuss the forwards flow, the backwards flow. I'll classify the ancient solutions, and in doing so, I'll show that there exists a new one-parameter family of homogeneous ancient solutions on spheres, which have the following behavior. So first of all, they have extra symmetry. They're invariant under a circle's worth of symmetries, and they can be viewed as submersion metrics for the Hopf vibration. So as time goes to minus infinity, the S1 fiber shrinks to a point, while the metric on the base on CPN varies. So one of these ancient solution collapses to the Fubini-Studi metric on the base. For this one, the metric on the base stays the same the whole time, and it's not so hard to see it's ancient. But the rest have a more complicated behavior, and as the fiber shrinks, the metric on the base varies, and these collapse to a second homogeneous Einstein metric on CPN found by Wolfgang Ziller. Okay. So a lot of this is motivated by the variational approach to finding Einstein metrics. So I'd like to discuss Einstein metrics for a little bit. Okay, so we say that Riemannian metric is Einstein if it has constant Ricci curvature. So if the Ricci tensor is a constant multiple times the metric. So Einstein metrics are in a way the nicest metrics we can hope to find on a manifold. Asking for constant sectional curvature is too strong because that implies our manifold is a space form, and a constant scalar curvature is too weak because we can achieve this even in a conformal class. So somewhere in the middle is constant Ricci curvature. And Einstein metrics are also nice because they satisfy a nice elliptic equation, and it turns out that they can be characterized variationally as critical points of a functional, which is what I would like to discuss now. So, given a compact manifold M, we can consider the space of Riemannian metrics on it, which we'll denote by M. And then we can define the total scalar curvature functional on the space of metrics, which assigns to a given metric the integral of its scalar curvature over the manifold. So if we restrict the total scalar curvature functional to the space of volume 1 metrics, then its gradient is minus the traceless Ricci tensor. And so critical points of the total scalar curvature functional have zero traceless Ricci tensor. So the Ricci tensor is a multiple of the metric. So critical points of the total scalar curvature functional are Einstein metrics. So since Einstein metrics are critical points of a functional, one might hope to use topological methods to prove their existence. For example, min-max methods. The problem with this, however, is that on the whole space of metrics, the total scalar curvature functional is not so well behaved. It doesn't satisfy, for example, the Palais-Smale condition, which one typically needs to use min-max methods. But as we'll see later, if we restrict to the space of homogeneous metrics, the total scalar curvature functional is more nicely behaved. So this is a natural place to search for Einstein metrics. Okay. So for the remainder of the talk, we're going to let M be a compact homogeneous space. So with G acting transitively and stabilizer at a point H. And we're going to suppose, moreover, that this compact homogeneous space is not a torus. So any homogeneous metric on a torus is flat. So this case is not interesting for us. Okay. And then we're going to consider the set of the subset of metrics for which the action of G is by isometries. So the subset of G invariant metrics or homogeneous metrics. And we're going to denote that space of metrics by MG1. Okay. So the space of homogeneous metrics turns out to be a nice finite dimensional manifold. It's actually a symmetric space and a fixed point set of an isometric action. And if we restrict the total scalar curvature functional to this to the space of homogeneous metrics, then since the scalar curvature of homogeneous metric is constant, the total scalar curvature is just the ordinary scalar curvature. And so critical points of the ordinary scalar curvature functional are Einstein metrics. Okay, and at this point, I'd also like to briefly mention the formula for the normalized Ricci flow on the space of homogeneous metrics for a compact homogeneous space. So it's given by, so the Ricci flow preserves isometry groups. And so we can restrict it to the space of homogeneous metrics. The normalized flow preserves volume and is equivalent to the Ricci flow up to rescaling and reparametrization. And on the space of homogeneous metrics, the normalized flow is twice the gradient flow of the scalar curvature, or also minus twice the traceless Ricci tensor. So at this point, we see that if we want to either control the behavior of the Ricci flow or guarantee the existence of Einstein metrics, it's going to be important to understand the global behavior of the scalar curvature functional on the space of homogeneous metrics. Okay. So now I'd like to get to our first existence theorem for Einstein metrics. So in 1986, Mackenzie Wang and Wolfgang Ziller proved the following. So they showed that if we have a compact homogeneous space, then the scalar curvature functional is bounded from above and proper if and only if the subgroup H is maximal in G. Okay, so what does this say? So this says that if there are no intermediate subgroups, then the scalar curvature functional is bounded from above and proper. So in particular, it achieves its maximum. That maximum being a critical point must be an Einstein metric. So this gives a topological reason for the existence of an Einstein metric. Another interesting thing that this says is that if the scalar curvature functional is not bounded from above, then there has to exist an intermediate subgroup. So somehow the intermediate subgroups in between H and G are going to play an important role in the global behavior of the scalar curvature functional. Okay, so what happens if there does exist an intermediate subgroup K in between H and G? Okay, so for any intermediate subgroup K, we can consider a fibration of homogeneous spaces, where the total space is G mod H, the fiber is K mod H, and the base is G mod K. Okay, and then what we can do is we can start with the metric on the total space, such that this projection is a Riemannian submersion, and such that the induced metric on this base is homogeneous. Then if we take such a metric, rescale the fiber by T, and then normalize so that volume is 1, we get a path of homogeneous metrics whose scalar curvature is given by this formula. So here in this formula, F is the dimension of the fiber, and the norm of A squared is the norm of the O'Neill tensor taken with respect to the initial metric. So the behavior of the scalar curvature as we shrink the fiber is going to depend on what this fiber looks like, on what K mod H looks like. So if K mod H is not a torus, then we can pick a metric on it with positive scalar curvature. For example, the one induced by the bi-invariant metric. So then this term is positive, and as we send t to 0, this term blows up, and the other terms go to 0. So if k mod h is not a torus, then we get a direction where the scalar curvature goes to infinity by shrinking those fibers. On the other hand, if k mod h is a torus, then any homogeneous metric on it is flat. And so the scalar curvature is 0. So this term goes away. And then as we send t to 0, everything else goes to 0. So then we get a direction where the scalar curvature goes to 0. And it also turns out that the traceless Ricci tensor goes to 0 as well, which is going to be important later on. Okay, so now I'd like to illustrate this behavior. So, so here's a picture of the graph of the scalar curvature functional over the space of homogeneous metrics under product of 2 3-spheres, where we've divided by the action of a circle of rational slope R sitting inside this product. Okay, so this homogeneous space turns out to be a circle bundle. So if we take a product of 2 Hopf vibrations, so S1 times S1 goes to S3 times S3, goes to S2 times S2, and then we divide by a circle of slope R, then this fiber just becomes a circle. And so our space is a homogeneous circle bundle. And by shrinking these fibers, we should get a direction where the scalar curvature and the derivative go to 0. And that's what we see here. So here's this direction where the scalar curvature goes to 0. Okay, there are also subgroups whose quotients are not tori. So this circle of slope R, it sits inside a 2 torus, and that 2 torus sits inside both S1 times S3 and in S3 times S1. So if we shrink in the direction of these subgroups, we should get directions where the scalar curvature goes to infinity, and that's what we see here. So these directions where the scalar curvature goes to infinity correspond to these subgroups. Okay, and just looking at this picture, we should be able to say a little bit about the behavior of the Ricci flow on this space. So the normalized Ricci flow in a compact homogeneous space, like we said before, was just twice the gradient flow for the scalar curvature. Okay, so there's this critical point over here, which is an Einstein metric. Here, you can't see it. Here, that's an Einstein metric. It's a fixed point of the normalized flow. If we start over here and we flow forwards by the gradient flow, we would expect the scalar curvature to go to infinity. Same thing if we start over here. Okay, on the other hand, since there's this unstable Einstein metric in the middle, there should be points nearby on the unstable manifold for it, where if we start and then we flow backwards, then it should take infinite time to reach that Einstein metric. So there should be nearby solutions where we flow backwards and we reach that Einstein metric in infinite time. So this gives us ancient solutions for the normalized flow. But it turns out that being ancient for the normalized flow is the same as being ancient for the Ricci flow. So this will give us ancient solutions for the Ricci flow. Okay, also if we start over here and then we flow backwards by the negative gradient flow, then the scalar curvature stays positive. So for such a solution, the scalar curvature stays positive. Then since the normalized flow is the gradient flow, the fact that the scalar curvature stays positive implies that we'll be able to continue it for all time. So this will give us another ancient solution. But this ancient solution will collapse along circle fibers, whereas these other solutions did not collapse. Okay.
Hey, Sammy, sorry to interrupt, quick question.
Yeah.
Why is it true that the ancient solutions for normalized flow are ancient in the unnormalized flow?
I'll talk about that a bit later. It actually uses one of your theorems. So it uses this fact that, yeah, I'll get to it later.
Okay, thank you.
Yeah. Okay. So yeah, this gives us an ancient solution for both the normalized flow and the Ricci flow, but it collapses. Okay, and also this Einstein metric in the middle, this unstable Einstein metric, we should be able to predict its existence from the fact that there are these 2 separate directions where the scalar curvature goes to infinity. So if we start with a point over here and a point over here, for example, and then we connect them by a path, and then we pull that path tight, we would expect to hit this mountain pass. So we got these directions where the scalar curvature goes to infinity from these subgroups. So somehow the structure of the set of intermediate subgroups, we should be able to use it to prove the existence of Einstein metrics using min-max methods. So this is the next thing I'd like to discuss. Okay, so what we can do is we can associate to a homogeneous space a graph. The vertices of that graph will consist of intermediate subgroups in between H and G. So say we have 3 intermediate subgroups in between H and G, say K1, say K2, and K3. Then the edges of this graph will correspond to containments between subgroups. So if K2 contains K1, then I'll draw an edge in between them. Then Christoph Bohm, Mackenzie Weng, and Wolfgang Ziller proved in 2004 that if this graph has at least 2 components, then there exists a critical point of the scalar curvature functional generically with co-index 1. So it's possible that the critical point is degenerate, in which case you can't say anything about the co-index, but in the non-degenerate case, it's co-index 1. Okay, so this critical point is an Einstein metric. So this gives you the existence of an unstable Einstein metric. And this is illustrated in this last picture. So in this last picture, there are these directions where the scalar curvature goes to infinity. And that implied the existence of this unstable Einstein metric in the middle. Okay. All right. So in order to prove this, to use these min-max methods, Bohm, Weng, and Ziller needed to show that the Palais-Smale condition is satisfied for the scalar curvature functional. So this is what they did. So they showed that the Palais-Smale condition holds for the scalar curvature functional, but only where you need it to hold. So they proved that the scalar curvature functional satisfies the Palais-Smale condition on the space of metrics where the scalar curvature is bounded away from 0, so say by epsilon. So that is for any sequence of metrics with bounded scalar curvature and the derivative going to 0, so traceless Ricci going to 0, it has a convergent subsequence. By continuity, that the limit of that subsequence will have to be Einstein because the traceless Ricci tensor is going to 0. Okay, so why is this Palais-Smale where you need it? Well, any Einstein metric on a compact homogeneous space necessarily has positive scalar curvature. It can't have negative scalar curvature because that would contradict Bochner's theorem, and it can't have 0 scalar curvature because then it would be Ricci flat. And a theorem of Alexievsky says that if you have a Ricci flat metric on a compact homogeneous space, then it's actually flat. So then our space would be isometric to a torus, which we assumed it's not. So so if we have an Einstein metric on a compact homogeneous space, the scalar curvature is necessarily positive. So if we're proving their existence variationally, we may as well assume a lower scalar curvature bound. Okay. So one interesting consequence of this theorem, besides being able to use it for the previous one, is that it tells you something about the moduli space of homogeneous Einstein metrics. So one consequence is that the space of G invariant Einstein metrics is compact. Okay. Okay, so Bohm, Weng, and Ziller also considered sequences of metrics which violate Palais-Smale. So we know that Palais-Smale holds when the scalar curvature is greater than epsilon. So such sequences are necessarily not bounded away from 0. So they considered sequences of metrics where the scalar curvature goes to 0 and the derivative goes to 0 as well. So traceless Ricci tensor goes to 0. And they called these metrics 0 Palais-Smale sequences. Okay, so first of all, note that such a sequence necessarily diverges. So if it converged, then by continuity, it would converge to an Einstein metric with 0 scalar curvature, so a Ricci flat metric. But then again, a Ricci flat metric on a homogeneous space is flat, and so then our space would be isometric to a torus, which we assumed it's not. Okay. And earlier we saw that one way to get such sequences is by starting with a homogeneous torus vibration, and then shrinking the fibers. So if we start with a homogeneous torus vibration and then shrink in the direction of the torus, we get such a sequence. But it turns out that this is, in a way, the only way to have such a sequence. So Bohm, Weng, and Ziller showed that a 0 Palais-Smale sequence exists if and only if there is an intermediate subgroup whose quotient is a torus. So this means that if you have a zero Palais-Smale sequence, then your homogeneous space is necessarily a torus bundle. So it's the only way you can get such sequences. Okay. So now I'd like to give an illustration of a zero Palais-Smale sequence. So this is the homogeneous space that we saw before, S3 times S3 mod a circle of slope R. And we saw before that it was a circle bundle. And by shrinking the circle fibers, we get this direction where the scalar curvature goes to 0. So just by taking a sequence of such metrics, this gives us a zero Palais-Smale sequence. Okay. So it turns out that we can say a little bit more about the geometry of these zero Palais-Smale sequences as the scalar curvature goes to 0. So in 2018, Francesco Pediconi proved the following. So he showed that a zero Palais-Smale sequence exists. So he showed that if you have a zero Palais-Smale sequence, then it asymptotically approaches a submersion metric for a homogeneous torus vibration with shrinking fibers. So more generally, he showed this for any divergent sequence of homogeneous metrics with bounded sectional curvature. Okay, so what does this say? So this tells us that along a zero Palais-Smale sequence, the metrics approach the metrics that we got earlier by starting with a nice metric on the total space of a torus vibration, and then shrinking in the direction of these fibers. So Pediconi's theorem tells us that this is what zero Palais-Smale sequences look like asymptotically as the scalar curvature goes to 0. So this theorem is going to be very useful later on when we classify the ancient solutions. Later on, we'll see that there are going to be some ancient solutions which converge to an unstable Einstein metric, and there'll be some ancient solutions where the scalar curvature goes to 0. And Pediconi's theorem will tell us what the geometry of these ancient solutions look like as the scalar curvature goes to 0. Okay. So now I'd like to discuss the Ricci flow on homogeneous spaces in general. So I introduced the normalized Ricci flow in a compact homogeneous space earlier, but in general, the formula for the normalized flow is given by this equation. So -2 times the Ricci tensor minus a term involving the total scalar curvature, which you introduce so that the normalized Ricci flow preserves volume. So the normalized Ricci flow, it preserves volume. It's equivalent to the Ricci flow up to a rescaling and reparameterization. And on a compact homogeneous space, since the total scalar curvature is just the scalar curvature, this term here just becomes the traceless Ricci tensor. And so on a compact homogeneous space, the normalized Ricci flow is just given by minus twice the traceless Ricci tensor, or twice the gradient of the scalar curvature. So fixed points of the normalized flow are Einstein metrics. Fixed points have 0 traceless Ricci tensor, and hence are Einstein metrics. Okay. So a lot of people have worked on the Ricci flow on homogeneous spaces. So Jorge Laure, for example, developed a bracket flow where instead of thinking about the metric changing along the Ricci flow, you fix an inner product, and then you view the Lie brackets as varying. This has been especially useful in the non-compact case. So for example, on nil manifolds and solved manifolds. And a lot of people have also worked on the dynamics of the Ricci flow on specific examples of compact homogeneous spaces, which is what I'd like to focus on now. So this is by no means a complete list of who's worked on what or joint papers. It's just to give a rough idea. Okay. So here's a nice picture from a paper by Nurlan Abiev and Yuri Nakhanarov, where they studied the Ricci flow on SU3 mod its maximal torus. Okay, so this is a picture of the normalized Ricci flow. So there are a few interesting things to note about this picture. So first of all, there are these 4 fixed points. These 4 fixed points correspond to Einstein metrics. This one in the middle is one induced by the bi-invariant metric on SU3. And these other ones are Kähler-Einstein metrics. The interior of the green region here represents the space of metrics with positive sectional curvature. The interior of the blue region represents the space of metrics with positive Ricci curvature, and the interior of the yellow region represents the metrics with positive scalar curvature. So we see here in this picture that if we start in the region of positive sectional curvature and then flow forwards, we lose that property in finite time. So metrics in the green region leave that region in finite time. And just by looking at this, this picture, we can also see that there's some ancient solutions. So here we have this Einstein metric of co-index 1, this unstable Einstein metric. So if we start nearby here on the stable manifold and then flow backwards, using the backwards flow, we arrive at that Einstein metric in infinite time. So this gives us an ancient solution for a normalized flow, which we'll see later means that it's also ancient for the Ricci flow. And similarly for this bi-invariant metric here in the middle, this one has a 2-parameter family of ancient solutions which converge to it as we flow backwards. Okay. So now I'd like to discuss a little bit about what's known in general for the Ricci flow on compact homogeneous spaces. So by Palais-Smale, there are 2 possibilities for the normalized Ricci flow. So the normalized Ricci flow is the gradient flow of scalar curvature. So the scalar curvature is increasing, and there are 2 possibilities. So either the scalar curvature remains bounded above. If the scalar curvature remains bounded above, then by Palais-Smale, the solution is going to have to converge to an Einstein metric as we flow forwards. The other possibility is that the scalar curvature is unbounded, that it goes to infinity. And in that case, the theorem by Wang-Ziller implies that there has to exist an intermediate subgroup in between H and G. And it turns out that in the second case, we can say a little bit more about the geometry of these solutions as the scalar curvature blows up. So Christoph Bohm in 2015 proved the following. So he showed that if we have a Ricci flow on a compact homogeneous space, then it develops a singularity in finite time. And moreover, that singularity is type 1. So in the sense that the norm of the curvature tensor, the norm of the curvature tensor blows up at most linearly near that singular time. And he showed also that under some further conditions, if we take a sequence of metrics, if we take a sequence of times converging to the singular time, and then we rescale the metrics by the scalar curvature, then these rescaled metrics, they subconverge to a product of a homogeneous Einstein manifold, so K mod H, times a flat Euclidean factor. So this K mod H is not just any homogeneous space, it's this K is a subgroup in between H and G. So if the scalar curvature blows up, it has to do so in a precise way. These rescaled metrics approach a product of a homogeneous Einstein manifold and a flat Euclidean factor. Okay. So now I'd like to discuss a little bit about what's known in the backwards case. So Ramiro Lafuente proved in 2012 that if you have a solution to the Ricci flow, and that solution has a finite backward singular time, so if it develops a singularity at a time minus t, then the scalar curvature has to go to minus infinity near that singular time. So that's the only way a solution can not be ancient for the Ricci flow. The scalar curvature has to go to minus infinity as you approach the singular time. Okay, and it turns out that being ancient for the Ricci flow is equivalent to being ancient for the normalized flow. So I won't say too much about the proof of this. One direction follows from the one direction. If you have an ancient solution for the Ricci flow, ancient solutions for the Ricci flow necessarily have non-negative scalar curvature, essentially by the maximum principle. And so the same is true for the corresponding solution of the normalized flow. So the solution for the normalized flow also has non-negative scalar curvature. And then we saw earlier that if we have if the scalar curvature stays positive, then we can continue the flow for all time. So this gives us an ancient solution for the normalized flow. And for the other direction, the main ingredient is this theorem by Lafuente. If it weren't ancient for the Ricci flow, then the scalar curvature would have to go to minus infinity. So I won't say much more about the proof of this. But as a consequence of this theorem in Palais-Smale, there's a dichotomy for ancient solutions. So if we have an ancient solution of the Ricci flow, it has to have non-negative scalar curvature. And so the same is true for the normalized flow. And then there are two possibilities for the scalar curvature. So either the scalar curvature stays bounded away from zero, in which case Palais-Smale tells us that the solution has to converge to an Einstein metric as we flow backwards. The other possibility is that the scalar curvature goes to zero, and then the derivative also goes to zero. So traceless Ricci goes to zero. In that case, we say that the ancient solution is zero Palais-Smale. So in this case, Petticone's theorem is going to tell us, in the second case, Petticone's theorem is going to tell us what these solutions look like as we flow backwards. So I'd like to just mention again that if we have a solution for the normalized flow with where the scalar curvature is positive, then it's necessarily ancient for the normalized flow and hence also for the Ricci flow. Okay. All right. So now I'd like to specialize to the case of homogeneous metrics on spheres. Okay. So besides the left invariant metrics on S3, the homogeneous metrics on spheres can all be described in terms of the Hopf vibrations. So there are the three Hopf vibrations, and associated to each Hopf vibration is a two-parameter family of metrics that we get by starting with a round metric on the total space. So we start with a round metric on the total space, and then we rescale the fiber by T, and we rescale the base by S. So this way we get a two-parameter family for each Hopf vibration, and this covers almost all the homogeneous metrics on spheres. But in the last case, in the Hopf vibration with S3 fibers, there's a larger family of homogeneous metrics, which we get by allowing the metric on the S3 fiber to be an arbitrary left invariant metric with eigenvalues, say, X, Y, and Z, instead of a round metric, which you would get if you just scaled it. And then the scale of the base is S. Okay. The Ricci flow on these two parameter families of metrics has already been studied. So it was studied by Maria Buzano and Ioannis Bakas, Shengli Kong, and Lei Ni. Once you normalize volume, these two parameter families become one parameter families. And you can understand the behavior of the Ricci flow in terms of the graph of the scalar curvature as a function of the scale of the fiber. Okay, so on the left is the graph of the scalar curvature for the Hopf vibrations with large dimensional fiber. So here the fibers are S3 and S7. And here on the right, this is, so in this picture, as we shrink the fibers, the scalar curvature goes to infinity because these guys are not toruses. And on the picture on the right, this is the graph of the scalar curvature for the Hopf vibration with S1 fibers. So in this picture, as we shrink the fibers, the scalar curvature goes to zero. Okay. Okay, so let's look at the picture on the left. For this picture, there are two Einstein metrics. So there's a round metric, and then there's a second Einstein metric. So just looking at this, we can see that there's some ancient solutions. So if we start over here to the left of the second Einstein metric and flow backwards, then we arrive there in infinite time. So this gives us an ancient solution for the normalized flow, which is hence also ancient for the Ricci flow. And same if we start here. So these guys are ancient. Okay. On the other hand, if we start over here to the right of the round metric and we flow backwards, then the scalar curvature becomes negative in finite time. So this guy is not ancient. And this round metric is a local maximum. So if we start nearby and we flow forwards, then we converge to this round metric under the forwards flow. Okay. Now for the picture on the right, we have a single Einstein metric, the round metric, and there's also a single ancient solution. So if we start to the left of the round metric and then we flow backwards, we start over here and flow backwards, then the scalar curvature stays positive. And this, together with the fact that the normalized flow is a gradient flow, implies that it's ancient for the normalized flow, and hence also ancient for the Ricci flow. Okay, on the other hand, if we start to the right of the round metric and we flow backwards, the scalar curvature becomes negative, so this guy is not ancient. But under the forwards flow, everything on the right converges to the round metric. So if we start over here, we converge to the round metric, and same thing as if we start to the left. Okay. All right, so now I'd like to discuss the behavior of the 4-parameter families. So now we consider the metrics that arise from the Hopf vibration with S3 fibers. So again, X, Y, and Z are the eigenvalues for the left invariant metric on the S3 fiber, and S is the scale of the base. So Wolfgang Ziller showed that among these metrics, there are only two Einstein metrics. So there's the round metric. The round metric, all the eigenvalues are equal to each other. And then there's Jensen's second Einstein metric. So for Jensen's second Einstein metric, the eigenvalues of the fiber are all equal. So the metric on the fiber is round. And the scale of the base relative to the fiber is 2n plus 3. Okay. So if we normalize volume to be 1, then this 4-parameter family becomes a 3-parameter family. And in this larger family of metrics, the round metric is a local maximum, and the second Einstein metric is a critical point with co-index 1 and index 2. So we already saw the co-index of the second Einstein metric in this previous picture over here. We see that this Einstein metric has some co-index, but in the larger family of metrics, it has some stable directions. So now I'll draw a graph, a 2-dimensional representation of the graph of the scalar curvature functional for these metrics. So here we have the metrics with extra symmetry. So those for which the metric on the fiber is round. So here we have the local maximum, the round metric, and then we have the second Einstein metric. Okay. So now the second Einstein metric has index 2. So the second Einstein metric has a 2-dimensional stable manifold. So here's a stable manifold. And it turns out that this stable manifold, it separates the space of metrics into 2 connected components. Any solution, any metric to the left of it, if we flow forwards, if we start over here and we flow forwards, then the scalar curvature goes to infinity in finite time. And any metric to the right of it converges to the round metric. Okay, so all these metrics to the right of the stable manifold converge to the round metric under the forwards flow. And it turns out that the theorem by Christoph Bohm that we discussed earlier, that implies that if we start to the left and the scalar curvature blows up, then the metric on the fiber approaches a round metric. So if we start to the left, then these solutions really approach this this curve of metrics that had these extra symmetries where the fiber was round. Okay, so this is the behavior of the forwards flow. The stable manifold separates the space of metrics into 2 connected components, namely those where the scalar curvature blows up and the metric restricted to the fiber approaches a round one, and any solution in the second component to the right of the stable manifold converges to the round metric in infinite time. Okay, so that's all I'd like to say about the forwards flow. So now I'd like to discuss the backwards flow, which is the case of main interest for us. Okay, so it turns out that that the ancient solutions for the Ricci flow, they have extra symmetry, and moreover, the eigenvalues have to satisfy these inequalities. So two of the eigenvalues on the fiber have to be equal, say y equals z, and the overall scale of the fiber has to be less than that of the base. So what these metrics look like is they look like Berger metrics on the fiber, where the scale of the fiber is just less than that of the base. Okay, so these solutions have an extra circle's worth of symmetries, and they can be viewed as submersion metrics for the Hopf vibration. Okay. All right. So as time goes to minus infinity, we can think about these solutions geometrically as shrinking the fibers of the Hopf vibration to a point while varying the metric on the base. So there's exactly one solution which collapses to the Fubini-Studi metric on the base, and the rest collapsed to a second homogeneous Einstein metric found by Wolfgang Ziller. Okay, so here's a picture of the normalized flow on the space of metrics with this extra symmetry, where y equals z. So this is the space of metrics where the ancient solutions all happen to live. So the flow lines here represent the backwards normalized flow. And we see that there are two fixed points, this round dot and this star. The round dot corresponds to the round metric, and the star corresponds to Jensen's second Einstein metric. The green line here represents the metrics with additional symmetry, so namely those where the fiber is round. So this green line is the two-parameter family of metrics that we saw earlier, and down here is the graph of the scalar curvature over this two-parameter family of metrics. So there's this solution over here, which corresponds to this region over here. Okay. So the red line in this picture corresponds to the stable manifold for the second Einstein metric. The arrows are going the other way because now we're looking at the backwards flow. The y-axis represents the ratio y over s. So the y-axis, it parameterizes the space of invariant metrics on the base, so on CPN. So we can think of the y-axis as the space of homogeneous metrics on the base. So as we move up and down in this picture, that corresponds to varying the metric on CPN. The x-axis here roughly corresponds to the length of the Hopf fiber. So moving to the right in this picture corresponds to shrinking the length of the Hopf fiber of okay. Okay, so these metrics over here at the end really lie at infinity, and they represent when the Hopf fiber has been completely shrunk to a point. So these metrics are Einstein metrics on the base, on CPN. So this dark square represents the Fubini-Studi metric, and this hollow square represents Ziller's second Einstein metric. And the ancient solutions are the ones in the closure of the blue region. So all these solutions in this blue region are the ancient solutions. Okay, so we see here that most of these collapse to Ziller's second homogeneous Einstein metric. So most of them approach this guy. And there's exactly one that collapses to the Fubini-Studi metric, and this one, the metric on the base, stays the same the whole time. Okay, and then there are these two non-collapsed ancient solutions, which converge to the second Einstein metric, and these are the ancient solutions that we saw earlier. Is this one and this one. Okay. So now I'd like to show you another picture of, so this is a picture of the graph of the scalar curvature functional when two of the variables are the same. So again, here we have this local maximum, that's the round metric, and then we have the second Einstein metric. In this picture, the ancient solutions are all the ones in this region. So all these guys are ancient solutions. And they're asymptotic to this red line, and they collapse to the second Einstein metric. This black line here represents the ancient solution that converges to the Fubini-Studi metric. And we can see from this picture that if we start back here, like behind the graph, and then we flow backwards, the scalar curvature becomes negative in finite time. So back here, these solutions are not ancient. And these solutions in this region are also not ancient, although it's not obvious just looking at this graph. Okay, so now I'd like to discuss the proof of this a little bit, that that these ancient solutions have to have this extra symmetry. So because being ancient for the Ricci flow is equivalent to being ancient for the normalized flow, it's enough to classify ancient solutions for the normalized flow. And then we saw earlier that there are two possibilities. So either the scalar curvature remains bounded away from zero, in which case our solution converges to an Einstein metric as we flow backwards, and it's non-collapsed, or the scalar curvature can go to 0, in which case we say that the ancient solution is 0 Palais-Smale. So there are these two possibilities. Okay, so if the solution converges to an Einstein metric, then by definition, it has to lie on the unstable manifold for one of these Einstein metrics. But the only Einstein metric with an unstable manifold was Jensen's second Einstein metric. And the unstable manifold was were these solutions here. So if we converge to an Einstein metric, then we have to be this solution or this solution, and the fiber has to be round. Okay. So then the other possibility is that the scalar curvature goes to 0. So if the scalar curvature goes to 0, then by Petticone's theorem, the solution asymptotically approaches a submersion metric for a homogeneous torus fibration with shrinking fibers. And it turns out that the only such possibility is the Hopf fibration. So it has to be the Hopf fibration. Submersion metrics for the Hopf fibration have two equal eigenvalues on the fiber. So what Petticone's theorem tells us is that this ratio y over z, it tends to 1 along the backwards flow. The other main ingredient is proving monotonicity for this ratio y over z. So we show that the ratio y over z actually has the opposite behavior that Petticone's theorem predicts. So along the backwards flow, the ratio y over z, it goes away from 1. So the only way it can converge to 1 if it's actually equal to 1 for all time. So you have to be equal to 1 in order to converge to it. So this tells us that the ancient solutions have to satisfy y equals z for all time. And so these ancient solutions are submersion metrics for all time. Okay, on the other hand, if the eigenvalues satisfy this inequality, so 2 of the eigenvalues are equal and the scale of the fiber is less than that of the base, then it turns out that these metrics actually have positive sectional curvature, and hence they also have positive scalar curvature. And we saw earlier that if we have positive scalar curvature preserved under the backwards flow, then our solution has to be ancient for the normalized flow, and hence also ancient for the Ricci flow. Okay. And a separate argument is required to show that if the scale of the fiber is larger than that of the base, then our solution is not ancient. So this uses a separate argument. Okay, so that's all I want to say about the proof. But now I'd like to discuss existence of ancient solutions in general. So earlier we saw that if we have an unstable Einstein metric, then it's straightforward to produce ancient solutions if we start on the unstable manifold for that Einstein metric. So whenever we have an unstable Einstein metric, we can construct ancient solutions, non-collapsed ancient solutions. But producing examples of collapsed ancient solutions is more delicate. So now I'd like to discuss existence in the collapsed case. So in the case where the scalar curvature goes to 0. So if there exists a collapsed ancient solution, then by Petticone's theorem, it has to collapse along toral fibers while approaching a submersion metric for homogeneous torus vibration. So if there exists a collapsed ancient solution, then our homogeneous space has to be a homogeneous torus bundle. So what happens if our homogeneous space is a torus bundle? So suppose that our homogeneous space is a torus bundle. So so total space G mod H, and the fiber here is just T, where this torus is a maximal torus inside the normalizer of H. Then we show that for every non-degenerate Einstein metric on the base, there exists an ancient solution which collapses to it as time goes to minus infinity. And moreover, we can bound the dimension of the space of such solutions below by the co-index of that Einstein metric on the base. So given an Einstein metric on the base, we get ancient solutions on the total space which collapse to it. Okay, so this generalizes the ancient solutions that we just discussed. So on the spheres, the ancient solutions collapsed along the fibers of the Hopf fibration, and they converge to an Einstein metric on the base. So in the sphere, they collapsed along the fibers of the Hopf vibration. And collapse to a metric on the base. And so if we look at the space of homogeneous metrics on the base, and we look at its scalar curvature, so here's a graph of the scalar curvature functional for homogeneous metrics on CPN on the base. So it looks like the picture we saw before. So here is the Fubini-Studi metric, and here is Ziller second Einstein metric. So this is the space of homogeneous metrics on the base. So then there are two Einstein metrics. So then this theorem predicts that there have to be ancient solutions which collapse to these two Einstein metrics. Moreover, this second Einstein metric is co-index 1. So this theorem tells us that there exists a one parameter family of ancient solutions which collapse to this Einstein metric on the base. Okay, so this explains the picture that we saw before. So before we had this with the Fubini-Studi metric, we had the second Einstein metric. There exists ancient solutions collapsing to each of these on the total space. And since the second one had co-index 1 on the base, there exists a one parameter family of ancient solutions which collapsed to it. So we had a one parameter family of guys collapsing to this one. Okay, so this theorem applies to many more examples, but now I'd like to illustrate a typical one. So, so we can view SU3 as a homogeneous torus bundle where T2 is a maximal torus. Okay, and down here again is the picture of the gradient flow for the scalar curvature functional on the space of metrics on the base. So this is the picture that we saw earlier from the paper by Abiev and Nikonarov. So on the base, we have these Einstein metrics. So the previous theorem tells us that on the total space, so on SU3, we get ancient solutions which collapse to these Einstein metrics on the base. Moreover, this Einstein metric on the base is co-index 2. So this is the normalized flow. So the arrows are going the opposite way, but this one has co-index 2. So the previous theorem tells us that there has to exist a two parameter family of ancient solutions on the total space which collapse to it. The same is true for these Einstein metrics. So for these Einstein metrics, the co-index is 1. So the previous theorem tells us that there exists one parameter families of ancient solutions on SU3 on the total space, which collapse along T2 fibers to these Einstein metrics. Okay. So now I'd like to end by discussing a theorem of Christoph Bohm, which suggests that there should be many more examples of collapsed ancient solutions. Okay. So in 2004, Christoph Bohm, he extended the ideas in the graph theorem that we discussed earlier. So he considered the following. So we can associate to a homogeneous space a simplicial complex. And the vertices of the simplicial complex will correspond to intermediate subgroups in between G and H. So say I have 3 intermediate subgroups. The edges, like before, they correspond to containments. Oh, I should also mention, these intermediate subgroups now, they have to contain the maximal torus. Okay, so they're in between the maximal torus and G. But okay, so the edges correspond to containments, just like before. So if K2 contains K1, then I draw an edge in between them. And if K3 contains K2, then I draw an edge between these as well. Now I have a chain of subgroups. So K1 is contained in K2, is contained in K3. So when I have such a thing, I draw a face in between them all. So then I connect them all by a face. So more generally, a P cell in this simplicial complex corresponds to a flag of subgroups of length P, where each subgroup is contained between the maximal torus and G. Okay, so what Christoph Bohm proved is he showed that if the simplicial complex associated to a homogeneous space is non-contractible, then there exists a G-invariant Einstein metric on your homogeneous space. The way he did this is by showing that if the kth homology of this complex is non-zero, then there exists a critical point of the scalar curvature functional, with co-index plus nullity equal to k. So in the non-degenerate case, it's just the co-index equals k. But in general, it's hard to control whether it's degenerate or not. So by construction, if we consider G mod the maximal torus times H, the simplicial complex of this homogeneous space is going to be the same as the simplicial complex of G mod H, because all these subgroups have to contain the maximal torus anyway. So if you look at its simplicial complex, it's the same. So whenever this theorem applies, it also guarantees the existence of a G invariant Einstein metric on the base. And that's what we needed to apply the previous theorem. So for the previous theorem, we need a G invariant Einstein metric on the base. So this suggests that there should exist many large parameter families of collapsed homogeneous ancient solutions. The only other thing that we need, which this theorem doesn't tell us, is that we need it to be non-degenerate. We need the Einstein metric on the base to be non-degenerate, which this doesn't exclude. But nevertheless, it suggests that there should be many examples. Okay, so that's all I wanted to talk about today. So thank you for listening.
Okay, thank you very much, Sammy. Very nice talk. It was definitely a very good picture of the whole situation. Are there any questions or comments?
Oh, there's something in the chat. I didn't see it.
No, it was just me pointing out that the picture was beautiful. Yeah.
Thank you.
I really liked your picture with the matrix with extra symmetry. Yeah.
Oh, thank you.
Yeah. By the way, I just have a quick question, but it's probably a very naive question, or maybe known already. I forgot. Is this special to the spheres case? The fact that the ancient solutions have extra symmetry, or do we know that they must have?
I don't know.
Extra.
Yeah, I only checked. It's only it was for the spheres. It had to do with the fact that we had this monotonicity for this ratio, which I don't see a reason for this to hold generally, but maybe it does, because this is typical for ancient solutions to have more symmetry. So maybe
Have you looked at known examples?
Not that much. It's definitely worth looking into. I should definitely do that.
Okay. Okay.
That'd be
yeah, it's an interesting question, right?
Yeah, for sure.
But yeah, very nice talk. Thanks.
Thank you.
Are there more questions or comments? Okay, if not, we say thank again to Sammy. Thank you.